Hi, in this presentation, our team will propose the design and development of two database solutions to store information for the upcoming Fitness 365 application for the MHL National Fitness Challenge. We will be implementing one relational database management system and one non-relational database system in order to recommend a suitable design for the database. The first database system that we will use is MySQL as our relational database. MySQL has an ACID consistency and thus suitable for data requiring a strict ACID compliance. Based on the CAP theorem, MySQL has a high consistency and availability, delivering a high performance in performing multi-row transactions. However, it requires a predefined schema to store the data, which we will explain later. To ensure a proof of concept, we took the additional effort in ensuring that our data is consistent throughout all entities by generating dummy data for some entities and then querying them to fill up other dependent entities. This is the EERD for relational database. First, we will start constructing a user social networks. There's a unary many-to-many relationship between a follower user and a following user. Hence, we need to introduce a weak entity, follower following, in order to break down this relationship. Since many users can join the same club and each user can join multiple clubs, we introduce user club as a weak entity to break down the many-to-many relationship between user and club. As each club also stores historical leaderboard data, it has multiple weekly leaderboard entities, hence a one-to-many relationship. To maintain referential integrity, each of the leaderboard positions user ID is a foreign key from the user. Since activity can be shared as a group, user activity will break down the many-to-many relationships. Each user activity may be activities with personal best timings. Hence, there's a one to optional one relationship between user and personal best. Each user can also give kudos and comments to any activities without any constraints. Hence, there's a relationship as such. Since many users can take part in the same challenge, and each user can take part in many challenges, user challenge entity is introduced to break down the many-to-many relationship over here. And it also stores the degree of completion of the challenge.
MongoDB was selected as the non-relational database solution for MHL. MongoDB uses a document-based data model and supports a dynamic schema. It can scale horizontally, and unlike MySQL, which offers strong consistency, MongoDB offers eventual consistency as it is sacrificed in favor of lower latency. In our project, the same set of sample data is used for both MySQL and MongoDB. Two collections are used, user activity and follower following. The collections used in our NoSQL implementation include user activity and follower following. Each document in user activity consists of the details of a user and the details of the activity that the user participated in, such as activity start time, activity distance, etc. It also includes an embedded array consisting of the user ID of the user, who gave kudos to the activity the user took part in, and the timestamp of the kudo given. Follower following consists of follower following relationships between different users. Each document consists of two users, their names, user IDs, and gender. Their follower following relationship is indicated as either yes or no. For data generation, random users, activities, clubs, challenges are manually generated. Then, associative entities such as follower following, user challenge, user activity are generated by combining various strong entity instances together. Subsequently, data for comment and kudo are then generated. Lastly, data for tables such as leaderboard and personal best are queried from existing tables and the results are inserted into them.
For SQL, user ID means the one being followed, while follower user ID means the one following the user. In this query, we need the gender and number of people the user is following. To do so, we need 4 nested select statements. Starting from the user table, we get the user IDs of female users. Next, we select the female users and name them as female following because the users represent the one being followed. We then group by follower user ID as we want the number of people that they are following. This part is then called number of female following. Similarly, this is repeated to get the number of male following by using the innermost select statement where gender equals to m. This part is then called number of male following. Afterwards, we join these two parts on the follower user ID. Hence, we get a number of males and females the person is following. Subsequently, we compare the number of female following and male following to ensure that the user is following more female users than male users. Lastly, we select these users from the user table where gender equals to M. For NoSQL, from the JSON document, we are only able to determine if the user is following and being followed by another user. Therefore, we do not have the count. To do so, we create 4 new fields: M following 1, F following 1, M following 2, and F following 2. M following 1 returns true if user 2 is being followed by user 1, and user 2 is a male, or false otherwise. F following 1 if user 2 is a female. M following 2 would be the other way around, with user 1 being followed by user 2. We also have 2 more fields. User 1 is male, and user 2 is male, to give 1 if the user is a male. We then create a temporary document called record. It is a nested array of information for user 1 and 2. This allows us to collate the number of male following and female following for each user. Afterwards, we unwind it and group the ID, sum the M following and F following. For isMale, using the first operator, we check and keep the first value of user is male. Lastly, we use the match operator to compare and ensure that the M following is less than F following and isMale equals to 1.
For SQL, firstly, we join the table follower following and the table user together on user.userid equals to follower following.follower user ID. This gives us the details of the followers, such as name, age, and gender. This is done to allow us to subsequently select by the gender of a user's followers. We then select rows with only female followers. This will give us all users who have female followers or both male and female followers. Since the set of female users with only male followers will not be in the set of users with both female and male or female-only followers, we select all female users from user whose user IDs are not in the list of user IDs we just obtained. This will give us the list of female users who are followed by only male users. For the NoSQL query, similar to the NoSQL part of question 2, we introduce a temporary document called record, which is a nested array of information for user 1 and 2. The fields are the same as question 2, M following 1, M following 2, F following 1, and F following 2. Another attribute user is female is made to check for the gender of the user being followed. We then unwind the record, group the ID, and sum the number of M following and M following. In this case, to get a list of female users who have only male followers, we ensure that isFemale equals to 1, the count for M followers is more than 0, and F followers is 0.
For query 4, we need to generate a list of users who follow each other mutually. For SQL, we join the same follower following table against itself by finding pairs of users where each party's user ID is the other party's follower ID. The n f1.userid less than f2.userid logic is important to avoid getting rows which actually contains the same pair. Not doing so will cause 2 pairs appearing with the order of the values under the 2 columns reversed. For the pair of user ID 1 and 5, we can see from here that 5 and 1 does not exist. For NoSQL, we look at the pairs of follower following and retrieve those with user 1 following user 2 true and user 2 following user 1 true. We then project both user IDs of each pair, sorted according to the ID, which has been pre-sorted in the data file in ascending order of user 1 and within user 1 in ascending order of user 2.
Query 5. Users are split based on the average weekly activity time. Since each user's activities occur over various number of weeks, this is calculated in a few steps. Firstly, activities are grouped by week number and user ID, giving us the active time for each user in different weeks. Next, these values are grouped according to user ID to determine the total active time of the user, as well as how many weeks he was active for. For example, if a user is only active for 2 weeks over the whole duration, his active time should be averaged over 2 weeks rather than the whole duration, which is around 5 weeks. Finally, we can calculate his average weekly active duration by dividing total time by number of active weeks. In SQL, 2 subqueries were used. The first subquery calculates each user's weekly active time in different weeks. This is done using a natural join of user activity and grouping entries by user ID and week number. This derived table is given the alias T1. The second subquery groups entries by user ID and calculates each user's total active time as well as number of active weeks using the count function. It is given the alias T2. The main query then calculates the average weekly active time of each user and uses a case statement which assigns each user a corresponding activity range from A to D. Subsequently, users are ordered by activity range, allowing us to obtain the following insights. As we can see, users 2 and 16 with activity range A are active for less than 30 minutes a week on average, and so on. In NoSQL, the aggregate function is used. The first step is to group the documents in the user activity JSON by user ID and week number, and obtain their active time in different weeks. A second group field is then used to group entries by user ID and calculate the total active time and number of active weeks. Average weekly activity time cannot be as simply created as in SQL. Instead, we need to use add field to process the total activity time and add the weekly average duration to each user's entry. Then, using the project field, conditional statements help us to assign each user activity ranges from A to D. Lastly, the final insights are obtained by grouping by activity range and returning a list of users in this category. As we can see, the same two users are active for less than 30 minutes a week on average. Queries 6 and 7 take generally the same approach for both SQL and NoSQL. One major difference in SQL is that because additional information is required, an additional natural join with the user table is required. For NoSQL, in order to access each user's age and gender after the group fields, it must be assigned to each user using an accumulator function. In our queries, the first function is used to assign each user the first value of age and gender corresponding to him or her. Besides this, the techniques used to further enrich the insights are essentially the same.
For query 8, we need to generate a list of users who have received more than 5 kudos on average for each activity. We need to link the users to the kudos that they have received. Since the kudos are tagged to activities that they have participated in, we join user activity consisting of user ID and activity ID, and kudo consisting of kudos based on activity ID. We then group them by the user ID. Based on the number of kudos each user received in total, divided by the number of activities he participated in, we selected those more than 5. For NoSQL, from user activity, we group the data based on user ID, number of activity count, and the number of kudo count. Recording the division of kudo count over activity count as count, we match those with count greater than 5. We then sort them according to user ID in ascending order.
For question 9, we'll be querying the monthly active social networks, which means to say, for each user, we'll be listing out their followers who have given them 5 or more kudos in each month for their activities. For the SQL query, we'll first need to perform a join between activity, user activity, follower following, and kudo. We will then convert the kudo timestamp to month using the month operator. Then, we will perform a group by the month of the kudo given, the user ID who is receiving the kudo, and the user ID who is giving the kudo. We then filter the groups using having operator to only select groups with a count of more than or equals to 5. For the NoSQL query, it will only involve the joining of 2 collections. First of all, we will unwind the kudo giver of each document in the user activity collection. Since it is unnecessary to include those kudos given by the users themselves in their activity, we will filter that off using the match operator here. Next, we will join the 2 collections using the lookup aggregate function. This can be done using an inner match operator that joins the user ID of the activity to user 1 if user 2 follow users 1, or to user 2 if user 1 follow user 2. Then we will filter the kudo givers again by selecting those that are in the following list using the match operator. Finally, we'll group it according to the activity user ID, the month in which the kudo was given, and the kudo giver ID, in order to obtain a count for each specific follower, giving kudos to a specific user on each month. We then use the match operator to obtain a count greater than or equal to 5 to give us the activity insight.
For SQL, we first use a subquery to find out for each user what's his weekly average activity distance and duration for the various spots. We name the output as T3. We then use another subquery to find out for each user's social network what's the group weekly average activity distance and duration for the various spots. We name the output as T4. Finally, we join together users, activities, T3 and T4. While we have used left joins for T3 and T4, we have to use cross join for activity, as it will provide all the possible week numbers and activity spots. For display purposes, we sorted the results by user ID followed by week number and activity spot. As can be seen here, for user ID 1 in week 28, he cycled an average time of 54.1 minutes and an average distance of 13.1 kilometers. In comparison, his network has cycled an average time of 54.9 minutes and an average distance of 14.0 kilometers. For NoSQL, because there's no cross-join, we have to break down our question into 2 parts. First, we find the weekly average activity distance and duration for the various spots on the per user level. We do this using an aggregation function, where we group the average of distance and duration using a composite ID, comprising a week number, user ID, and the activity spot. Then, we slowly layer our output by pushing part of the ID into the output. As we push, we sort our data at the same time. In the final output, we have groups sorted by week. Within each week, the list of users is sorted. Within each user, we can see his activity details in that week. Next, for the second part, we have to find the same information but on a per user network basis. We can do this using an aggregation function as well. We first add two fields containing Boolean values, which represents if user 1 is following user 2, and if user 2 is following user 1. We make them into a record before unwinding it. We then apply a filter where the following condition equals true. Finally, we can group by user ID to see for each user who does he follow. We then unwind this array before using lookup to join the user activity to bring in the activity data for the users who are being followed. Subsequently, we can follow our steps from the first part to find the average activity distance and duration on the network level before we layer our data in the same manner. We managed to achieve the same results between SQL and NoSQL. For example, for user ID 1 in week 28, he cycled an average time of 54.1 minutes and an average distance of 30.1 kilometers, whereas his network cycled an average time of 54.9 minutes and 40.0 kilometers.
Our recommendation to MHL is that they should use NoSQL over SQL. Our reasons are as follows. Firstly, rapid data growth and scalability. Citizens are expected to use the app frequently for a prolonged period, and app usage is expected to be highly intensive during weekends and weekday evenings. As such, a lot of usage data, like following follower relationships, user activities, and the associated kudos will be generated. If we use a relational database, it has to scale vertically, meaning that the information has to keep migrating to faster networks with larger hard disks. Whereas for NoSQL, its decentralized nature will allow us to scale horizontally, meaning that we can distribute our data and the associated computation across multiple servers. This means that the hardware requirement for each individual server is not so demanding.
The second advantage that NoSQL has over SQL is that it supports concurrent performance. In designing the database, we also take into account that this database is most likely to be accessed, meaning read and write, by multiple users at any one time. If we were to use an RDBMS, update is done in a transactional way. Before every update, the RDBMS has to use a locking mechanism to mark the data so that no other process can modify it until the update finishes. Such a locking mechanism will make it difficult for multiple users to update the database at the same time, as they will have to wait for the update requests before them to be serviced first, before their update request can be processed. Whereas for NoSQL, there is no enforcing of the transactional integrity, meaning that the high volume of users can write to the database concurrently.
And finally, non-relational database has flexible data requirements. We need to take into account the possibility of the need for us to change the database structure in the future. And again, using NoSQL will make it easier for us to do that. Traditional relational database relies on static data structure, and a database schema has to be established well before any coding can begin. As such, if we want to change the database structure later on, it is going to be time-consuming and expensive. In contrast, NoSQL can handle an ever-changing data model because there is no database schema to start with, meaning that it can handle constantly changing and evolving data that we might not be able to foresee now. Admittedly, this results in problems with data consistency and reliability as compared to relational databases with strict schema templates. Based on the context of being a fitness mobile app similar to social media, there are no critical data that requires strict exit compliance.
However, NoSQL has certain disadvantages, as it is a relatively new system as compared to SQL. As such, it has limited functionalities. For example, in question 10, SQL's alter join function allows us to output the two subqueries side by side. However, NoSQL is unable to do this, as the closest command is lookup, which is equivalent to a left join in SQL. Thus, two separate queries were required for NoSQL. Nevertheless, we expect that with ongoing development of NoSQL, such functionalities will be added in due time, eventually making it as functional as SQL, but with higher performance, scalability, and flexibility.
Also, queries in NoSQL require specific JSON documents that are tailored to the purpose. Else, the NoSQL query will be very complicated, as shown in our following queries in question 2, 3, 9, and 10. In comparison to NoSQL, SQL queries do not require tailor-made data structures due to the relative simplicity of SQL. MHL has to determine a balance between increasing the complexity of connections and the complexity of queries. For example, if more reads will be expected than writes, MHL can consider increasing the complexity of the collections by adding more embeddings to allow for faster and more convenient reads. Conversely,
If more updates are expected than needs, MHL can consider reducing redundancies in the collection to expedite updates. To conclude, we are confident that our non-relational database implementation and queries are capable of handling both the current and future needs of the Ministry of Healthy Living in better understanding citizens' activeness and lifestyles.